Right now, you are falling. You are not sitting in a chair, standing still, or looking at a screen. From the perspective of fundamental physics, you're in a state of continuous motion through a hole in space, a colossal structure 2 billion light years wide. This is not a metaphor or science fiction, it is a confirmed astronomical fact, established with high precision in 2013, and most people on the planet still have no idea about it. We live inside a giant cosmic void, officially named the KBC Void after its discoverers, Keenan, Barger, and Coy. This is not just an empty space between galaxies, it is a true cosmic desert where the density of matter, both visible and dark, is 20% lower than it should be, according to all our proven models of the universe. This vast nothingness, this cosmic hollow in which we find ourselves, is not a passive backdrop. It actively distorts our measurements of reality itself. Because of it, the universe in our corner of space appears to be expanding faster than anywhere else. This effect is so strong that it breaks our most fundamental equations describing the evolution of the cosmos and creates what the world's leading scientists, without exaggeration, call a crisis in cosmology. In this video, we will embark on a journey that begins with a simple, almost routine count of galaxies, and ends with a complete rethinking of our true place in the universe. We will explore the physical reasons why 90% of the volume of the entire observable cosmos is empty, and reveal what it really means to exist on the cosmic backwater, inside a statistical anomaly that, according to our theories, should not have appeared. We will examine how this emptiness offers a shocking but elegant solution to the main mystery of modern astrophysics, while simultaneously challenging one of the most unshakable philosophical principles of science, the principle of ordinariness. If you are ready to see the universe in a completely different way, as cosmologists who have encountered an insoluble contradiction see it, get ready. Our investigation begins. But how did we, inhabitants of a tiny rocky planet, orbiting an unremarkable yellow star on the edge of an ordinary spiral galaxy, end up at the center of such a special and anomalous region? And why might this shocking discovery be the only key to the greatest mystery in modern physics? Imagine you have two of the world's most accurate industrial thermometers, each costing $1 million. One, based on the principles of atomic spectroscopy, you lower into a tank of boiling water, and it reads 100 of a degree Celsius. The other, which uses laser interferometry, you place in the same tank, and it reads 91 degrees. Both devices have undergone every conceivable calibration at the world's best metrology institutes. Both, according to their creators, are completely reliable and based on fundamental, well-studied principles. What conclusion would you draw? Either one of the thermometers, despite all the guarantees, is systematically faulty, or your understanding of the physics of water boiling is fundamentally incorrect. This is precisely the seemingly absurd situation in which modern cosmology finds itself. Its main measuring instrument, its thermometer for the universe, is the Hubble Constant, or simply H0. This number tells us how fast the universe is expanding, and we have two independent, incredibly accurate ways to measure it, based on different physical principles and different eras in the life of the universe. The first way is to look at the nearby or modern universe. We find objects in the universe with known absolute luminosity, so-called standard candles. Ideal candidates are Cepheids, pulsating stars whose pulsation period is strictly related to their brightness, and Type Ia supernovae, thermonuclear explosions of white dwarfs, which always have almost the same luminosity at their peak. By measuring their apparent brightness in the sky, we can accurately calculate the distance to them. Then, by measuring their redshift, the stretching of light waves due to the expansion of space, we can determine their speed of recession from us. By comparing this data for hundreds of such objects, we obtain a local value for the Hubble Constant. The best modern measurements, conducted by teams such as SH0ES, consistently give a result of about 73 kilometers per second per megaparsec. This means that for every 3.26 million light-years of distance from us, the expansion rate of the universe increases by 73 kilometers per second. The second method is to look deep into the past, into the childhood of the universe, by studying the cosmic microwave background, CMB. This is light left over from the Big Bang, emitted when the universe was only 380,000 years old. Spacecraft such as Planck have created an incredibly detailed map of this ancient light. This map contains information about the initial parameters of the universe, its density, composition, and initial expansion rate. We can take these parameters and, using our standard cosmological model, the Lambda-CDM model, which brilliantly describes the evolution of the cosmos, calculate what the expansion rate should be today, 13.8 billion years later. And this method gives a completely different answer, incompatible with the first, about 67 kilometers per second per megaparsec. The discrepancy is 9%. This is not a tiny error that can be attributed to measurement errors. It is a huge gap. The statistical significance of this discrepancy has reached the 5 sigma level. In physics, this means that the probability of a random coincidence is less than 1 in 3.5 million. This is the gold standard for announcing a new discovery. This discrepancy is known as the Hubble Tension, and it tells us something very unpleasant. Either our most proven measurement methods or our most successful model of the universe are fundamentally wrong. Either our rulers or the universe itself is lying. A scientific crisis of this magnitude always opens up 2 possible paths. The first, most exciting and desirable for many physicists, is the path of new physics. Perhaps Hubble's tension is the first warning sign that our standard cosmological model is incomplete. Maybe dark energy does not behave as we thought it did, changing over time. Perhaps there are new, unknown particles, such as sterile neutrinos, that influence the expansion of the early universe. Or, even more radically, perhaps Einstein's theory of gravity itself needs to be modified on cosmological scales. All of these hypotheses are actively discussed, but they all require the introduction of new entities and complicate the existing, elegant, and proven model. But what if there is a second way? What if the answer lies not in exotic new physics, but in something much simpler, yet philosophically uncomfortable? What if the problem is not with our theories or our measurements, but with ourselves, or more precisely, with our location? This idea, known as the local void hypothesis, offers a stunning explanation. The Hubble crisis is an artifact, a systematic error caused by the fact that we are conducting our closed measurements while inside a giant cosmic anomaly, the very KBC Void. This hypothesis puts forward not unknown laws of nature, but our local environment as the main suspect in our cosmological detective story. It claims that, on average, the universe is indeed expanding at a rate of 67 kilometers per second per megaparsec, as predicted by the model based on relic radiation data. However, being in an area of reduced density, we experience additional acceleration away from the center of this void. When we measure the velocities of nearby galaxies, we measure the sum of these 2 effects: global expansion and local outflow. And this sum is exactly what gives us the observed 73. Thus, the crisis disappears. Both measurements are correct. They simply measure different things. One measures the global average velocity, the other measures the local velocity, contaminated by our motion. This idea is elegant. It does not require rewriting physics textbooks, but it requires us to accept that our position in the universe is special. And this undermines the cosmological principle on which all modern cosmology is based. To understand how this void became the main suspect in our case, and how strong the evidence against it is, we need to return to the moment of its unexpected and almost accidental discovery. The discovery of the KBC Void was not the result of a targeted search for anomalies. It arose from routine, painstaking work cataloging the universe. In 2013, 3 astronomers, Ryan Keenan of the University of Hawaii, Amy Barger of the University of Wisconsin, and Lennox Cowie, also of the University of Hawaii, were engaged in a fundamental task: compiling a three-dimensional map of the distribution of galaxies. Their goal was to test how homogeneous the universe is on a large scale. Using data from a variety of independent sources, including the Sloan Digital Sky Survey, SDSS, and other redshift catalogs, they analyzed the positions and distances of tens of thousands of galaxies. The method was simple in essence: divide the sky into sections and count how many galaxies are in each cube of space at different distances from Earth. The cosmological principle, a fundamental assumption of modern science, states that if you take a large enough volume of space, the universe should look roughly the same everywhere. Of course, there are local clusters and voids, but on average, the density of matter should be constant. When researchers began to analyze the data, the numbers did not add up. In the universe close to us, within a radius of about 1 billion light years, there was a systematic shortage of galaxies. In every direction they looked, the number of galaxies observed was significantly lower than predicted by the standard model. This was not a small fluctuation. The matter deficit was about 20%. Imagine conducting a census in a large city and finding that in the central district where you live, there are 20% fewer people than the city average, and this deficit persists for many kilometers around. The first reaction was to think there was a mistake. Scientists double-checked their calculations, used different calibration methods, and took into account the possible influence of interstellar dust, which could hide distant galaxies from us. They brought in data from different telescopes observing the sky in different wavelength ranges, but the result remained unchanged. Around us, in all directions, stretched a giant sphere of cosmic emptiness. Our own Milky Way galaxy and our entire local group, including the Andromeda Galaxy, are located inside this huge, low-density bubble. This was not just another void between galaxy clusters, of which there are many. It was a structure of monumental scale, 2 billion light-years across, the largest void known at the time, and one in which, by coincidence, we find ourselves. This was not just a discrepancy in the numbers, it was direct evidence that we are in a very, very special place. But how special is it? And could simple bad luck explain our situation? To understand how anomalous our situation is, cosmologists turn to their most powerful tool: computer modeling. Using the standard cosmological model known as Lambda-CDM, LCDM, they can recreate the evolution of the universe from the first moments after the Big Bang to the present day. This model is incredibly successful. It predicts with remarkable accuracy the observed structure of the cosmic microwave background, the chemical composition of the early universe, and the overall distribution of galaxies in the cosmic web. The LCDM model is the foundation on which all modern cosmology rests. And here's what happens when we ask this model to create a universe similar to ours. Scientists run thousands of simulations on supercomputers. Each simulation is a new virtual universe, born with random initial quantum fluctuations, which then evolve under the influence of gravity and dark energy over 13.8 billion years. These simulations always result in a cosmic web, a complex structure of dense filaments and giant voids. But when scientists begin to search these virtual worlds for voids comparable in characteristics to the KBC, that is, with a radius of 1 billion light years and a density deficit of 20%, they find virtually none. The probability of such a giant and empty structure forming randomly within the LCDM model is negligible. Different studies give slightly different figures, but they all point to one thing. Our position is a statistical miracle. Some estimates suggest that such a void is a 3 sigma deviation from the mean, which means a probability of about 1 in 370. Other, more recent analyses indicate a 5 sigma deviation. In particle physics, a 5 sigma result is the threshold at which a new discovery is announced, an event that cannot be a coincidence. We live within a structure that, according to our best and most proven theory, simply should not exist. This presents the scientific community with a very unpleasant choice, which in science is called the fine-tuning problem. Either we are incredibly, fabulously lucky to find ourselves in one of the rarest areas in the entire observable universe. Or our fundamental theory of the universe, the LCDM model, has a fatal flaw. It may correctly describe the universe on average, but systematically err in predicting the largest structures, the most extreme fluctuations. It's like having a perfect climate theory that brilliantly predicts the average temperature on the planet, but is unable to predict the existence of Category 5 hurricanes. And we, in fact, live in the center of one of these cosmic mega-hurricanes. At first glance, the existence of voids is not surprising. If we look at a map of the distribution of galaxies on the largest scales, we see that the universe is not uniform at all. It has a honeycomb, sponge-like structure that astronomers call the cosmic web. It is the largest structure in nature. It consists of dense threads, or filaments, that stretch for hundreds of millions of light years. Along these threads, like beads on a string, are groups and clusters of galaxies. Where the threads intersect, massive superclusters form, giant cities of the universe, containing thousands of galaxies. Between these dense structures lie voids, or voids. They occupy the vast majority of the volume of space, about 90%, but contain a negligible fraction of its mass. The universe is like Swiss cheese, where matter is the cheese itself and voids are the holes. Or, to use a more accurate analogy, it is like foam, where dense walls of soap solution surround large air bubbles. This grandiose architecture was not obvious from the outset. For a long time, astronomers saw only a two-dimensional projection of galaxies on the celestial sphere. It was only in the 1970s and 80s, with the advent of mass surveys of redshifts that allowed accurate measurements of distances to thousands of galaxies, that the three-dimensional structure of the cosmos began to emerge. The pioneers in this field were scientists such as Margaret Geller and John Hooker, whose maps revealed the Great Wall, a colossal structure of galaxies, to the world for the first time. But this structure does not explain our anomaly. On the contrary, it only exacerbates it. The cosmic web is a hierarchical structure. There are small voids, tens of millions of light years across. There are medium ones, 100 to 200 million light years across. They are the norm. They easily arise in computer simulations. But the KBC Void, with its diameter of 2 billion light years, is a structure of a completely different order. It is so large that it could contain thousands of normal voids. It violates the very principle of hierarchy. It is as if, among the usual soap bubbles in the foam, a single giant bubble suddenly formed, occupying half the volume of the entire bathtub. Its existence would require some special, non-random formation process. Thus, the very fact of the existence of the cosmic web does not save our standard model. On the contrary, a detailed study of this structure shows how much we deviate from the general picture. Why is our hole in Swiss cheese so incredibly, statistically abnormally large? To answer this question, we need to delve into the strange physics that governs the behavior of matter within these cosmic deserts. Inside the cosmic void, gravity behaves like a traitor. The fundamental law of the universe, the very force that gathered dust into stars, bound stars into galaxies, and holds these galaxies in clusters, begins to work in reverse. It does not pull matter toward the conditional center of the void, but effectively pushes it outward. This effect is not a violation of the known laws of physics, as it may seem at first glance. No new repulsive forces are at work here. On the contrary, this is their most frightening and counterintuitive consequence, born in conditions of extreme mass asymmetry. To untangle this paradox, we need to stop thinking of gravity as a simple force pulling everything to a single point, to the center of mass. Instead, let's imagine it as a relief, a gravitational landscape consisting of valleys and hills, as described by Einstein's general theory of relativity. Massive clusters of galaxies, walls, and filaments of the cosmic web are deep gravitational valleys or wells. Matter, like water, naturally flows into them, gathering into dense, gravitationally bound structures. And what is the void in this landscape? Intuition suggests that it must be the deepest pit, the lowest point. But the opposite is true. Cosmic emptiness is the top of a very gentle, almost flat gravitational hill. It is an area of space with increased gravitational potential. Now, imagine that you have left a bowling ball at the top of such a giant, almost flat hill. The force pulling the ball toward the geometric center of the hill is practically zero, because there is very little mass beneath it. But on the horizon, on all sides, you see massive mountain ranges. These are the walls and filaments surrounding the void. Where will the total resulting force of gravity be directed? It will pull the ball away from the nondescript center of the hill toward these distant but immeasurably more massive mountains. The ball will begin to slowly but steadily roll down the hill toward the nearest gravitational valley. Galaxies inside the KBC Void behave in exactly the same way. They are not attracted by the sparse center of the void itself, but by dense superclusters, such as the Shapley supercluster, which are far beyond its boundaries. This process is called gravitational outflow. The void itself does not push anything out, but the geometry of space-time around it creates conditions in which everything inside is doomed to escape. Gravity has not changed its nature, it always attracts. But in the asymmetric environment of the void, the point of greatest total attraction is not inside, but outside. This mechanism is the key to our entire investigation. It turns a static hole in space into a dynamic engine that determines the motion of hundreds of thousands of galaxies, including our own. It is this outflow that creates the very cosmic mirage that, as we shall see, is capable of completely explaining the Hubble crisis and distorting our most accurate measurements of the universe. Let's reinforce this counterintuitive idea with a more down-to-earth analogy. Imagine a large but very shallow pool, almost empty, with a water level of only a few centimeters. This is our void. And around this pool are several huge tanks filled to the brim with water. These are massive superclusters of galaxies. Now, if you make a small hole in the wall of one of the tanks, where will the water flow? Into the pool, of course. This is analogous to how matter is pulled into gravitational valleys. But what will happen to the water that is already in our shallow pool? It is affected by Earth's gravity, pulling it down. But if we imagine that the reservoirs around it are so massive that their own gravity is comparable to Earth's gravity, then the water in the shallow pool will begin to be pulled towards these reservoirs. That's the point. Galaxies within the void, like that thin film of water in the pool, roll away toward the more massive structures, the mountains or reservoirs that surround the void. We are not pushed out by the void itself, but rather attracted by everything beyond it. This effect of gravitational outflow is not a hypothesis, but an observed fact. And this rolling away has a quite measurable and, moreover, shocking speed. Understanding this analogy is critically important because it translates the problem from the realm of abstract mathematics of general relativity to the realm of visual physics. The force acting on any object inside the void is the vector sum of all gravitational forces from all masses in the universe. In a homogeneous universe, this sum would average out to zero. But in our real, structured universe, where we are inside a giant mass deficit, this sum is not zero. It has a distinct direction, outward, away from the center of the void. This imbalance of forces is the engine of our local motion. It explains why we cannot consider ourselves resting observers, even in relation to the relic radiation that serves as a universal reference frame. We are in a gravitational draft, and this fact changes everything. This gravitational draft is not just a theoretical effect. It can be measured. And when astronomers did so, the result was staggering. Our own galaxy, the Milky Way, along with the entire local group, is hurtling through space at a speed of approximately 627 kilometers per second. That's almost 2.5 million kilometers per hour, or 600,000 miles per hour. This speed has nothing to do with the overall expansion of the universe, which stretches space itself. This is our own peculiar velocity. The speed of movement through space relative to a universal reference frame set by relic radiation. Where does this gigantic speed come from? It is the sum of several gravitational vectors. We are partially attracted to the nearest large cluster, the Virgo cluster. An even more powerful attraction comes from the so-called Great Attractor, a concentration of mass hidden behind the dust of the Milky Way. And our entire structure, the Laniakea supercluster, in turn, is moving towards the even more massive Shapley supercluster. But a significant part of this speed, according to scientists' estimates, is the very outflow caused by the mass deficit behind us. We are literally running away from the center of our local void. This velocity is not chaos. It is the most important piece of evidence in our investigation. It directly links our main suspect, the KBC Void, to the main crime, the Hubble crisis. Why? Because if we are moving at such a tremendous speed, this movement must inevitably affect our measurements of the speeds of other distant galaxies. It's like trying to measure the speed of oncoming cars while riding on a train that is itself traveling at tremendous speed. You have to subtract the speed of the train very precisely to get the true speed of the cars. In cosmology, astronomers have long learned to make corrections for our motion, but the vacuum effect turned out to be much larger and more complex than expected. It creates not just our local motion, but a coherent bulk flow involving hundreds of thousands of galaxies in a huge volume of space. Ignoring this flow means introducing a systematic error into all our local measurements of the expansion of the universe. And the size of this error, as it turns out, may be just what is needed to explain the whole mystery of Hubble tension. Now we have reached the climax of our investigation, the moment when all the evidence converges at a single point. We have established that the universe is lying to us about its expansion rate. We have identified the prime suspect, the giant KBC Void, and we have found the murder weapon, the gravitational outflow that is causing us to race through space at tremendous speed. It is time to put it all together and understand the mechanism of the cosmic mirage. When astronomers measure the Hubble constant using the local method, based on supernovae and Cepheids, they are essentially solving a simple equation: speed, h0 x distance. They measure distance using standard candles and measure speed by redshift. Then they calculate h0. But that's where the catch lies. The redshift we observe in a distant galaxy is not simply the result of the global expansion of the universe. It is the sum of two effects. The first is cosmological redshift, caused by the stretching of space itself. This is what is related to the true global Hubble constant. The second effect is the Doppler redshift caused by our own peculiar velocity relative to this galaxy. If we are moving away from the galaxy, its light is further stretched and becomes redder. If we are moving towards it, the light is compressed and becomes bluer. And as we have already established, we are moving. Very fast, in fact. And most importantly, not chaotically, but as part of a coherent flow directed away from the center of the void. This means that for most of the galaxies we observe, our speed of escape from the void is added to their cosmological expansion speed. As a result, their total observed speed is systematically overestimated. When we substitute this overestimated speed into the equation, we get an overestimated value of h0, the very same 73 km/s. This is the essence of the cosmic conspiracy hypothesis. The void creates a local Hubble Bubble, an area of space where all measurements of expansion velocity are systematically distorted by our own motion. We look at the universe as if through a crooked mirror in a funhouse. The mirror does not change the objects themselves, but distorts their proportions. Similarly, the void does not change the laws of physics, but distorts the results of our measurements. We are not measuring the true global expansion velocity. We are measuring the sum of that velocity and the velocity of our local gravitational outflow. And this simple but powerful idea has the potential to completely change our view of one of the deepest crises in modern science. So could this cosmic mirage be not just a qualitative explanation, but a quantitative solution to the problem? Can we calculate exactly how much the outflow from the KBC Void contributes to our measurements? And will this contribution coincide with the missing 9% difference? According to the work of several independent research groups, the answer is yes, it can. Using complex computer models that take into account the observed size and depth of the KBC Void, as well as the distribution of masses beyond it, scientists can calculate the expected rate of gravitational outflow at our point. The results show that this effect is capable of creating an additional, apparent component of expansion, which accounts for 5 to 8% of the total value. This is enough to explain most, if not all, of the observed discrepancy between 67 and 73 kilometers SEMST. The Hubble crisis can be resolved without any new physics. There is no need to invent evolving dark energy or exotic particles. It is enough to simply take into account the fact that we live in a statistically anomalous but physically understandable place. This solution has scientific beauty and is consistent with Occam's razor. One should not multiply entities unnecessarily. Why invent new laws of nature when the old ones, applied in the right context, do a fine job of explaining the observations? The void hypothesis is not a revolution, but rather a counter-revolution. It brings us back from speculating about new physics to taking a closer look at our local environment. It tells us, before declaring that all of physics is wrong, make sure you have calibrated your instruments correctly, taking into account that your laboratory is hurtling through space at 2 million kilometers per hour. This turns the whole problem upside down. Perhaps the Hubble tension is not the first sign of the collapse of the standard model, but on the contrary, its greatest triumph. After all, it is this model, describing gravity and the formation of structures, that predicts the existence of voids and outflow effects. But if everything is so simple, elegant, and logical, why has the scientific community not yet accepted this idea as the final solution? Why does the debate continue with unabated force? The answer to this question lies not so much in the realm of physics, as in the realm of the philosophy of science. Many scientists instinctively and consciously resist the vacuum hypothesis because it violates one of the most fundamental and fruitful principles in the history of science, the cosmological principle, also known as the Copernican principle. This principle, in its modern formulation, states that the Earth does not occupy any special, privileged position in the universe. On a sufficiently large scale, the universe is homogeneous and isotropic, meaning it looks the same everywhere and in every direction. This is not just a beautiful idea, it is a powerful working tool that allows us to apply the laws of physics discovered on Earth to the rest of the universe. The entire history of astronomy, starting with Copernicus himself, is a history of the gradual decentralization of humanity. First, we realize that Earth is not the center of the solar system. Then, that the Sun is just one of billions of stars on the edge of the Milky Way. Then, that our galaxy is just one of hundreds of billions in a universe that has no center. The principle of mediocrity, the idea that we are unremarkable observers in an unremarkable place, has become deeply ingrained in the scientific worldview. Now, the KBC Void hypothesis invites us to take a step back. It does not say that we are the geometric center of the universe, but it does claim that we are in an observationally privileged, statistically extremely rare place that systematically distorts our conclusions about the cosmos. To accept this hypothesis is to acknowledge that we live in a special place. This is a philosophically uncomfortable idea for many physicists. It borders on the so-called anthropic principle. The idea that the universe is the way it is because otherwise we would not be here to observe it. Most physicists prefer explanations that do not depend on our specific existence or location. They seek universal laws that would be true for any observer anywhere in the universe. Therefore, for them, the hypothesis of new physics seems preferable. It is better to assume that our laws are incomplete than to admit that our location is unique. This philosophical barrier is one of the main reasons why the debate continues. It is a battle between two worldviews. The elegance and simplicity of physical laws versus the universality and ordinariness of our place in the universe. But what ultimately creates this grandiose structure of voids and walls, which has become the arena for this battle of worldviews? What is the invisible conductor that controls the distribution of matter in space? The answer to this question is dark matter. It is a mysterious substance that does not emit, absorb, or reflect light, making it completely invisible to all our telescopes. We know of its existence only because of its gravitational influence. It is dark matter, which makes up about 85% of all matter in the universe. That is the invisible framework, the gravitational foundation on which the entire cosmic web that we see is built. The ordinary baryonic matter that makes up stars, planets, and you and me is just light dust settled on this massive, invisible structure. The process of forming this structure began with tiny quantum fluctuations in the first moments after the Big Bang. These fluctuations created barely noticeable irregularities in the distribution of dark matter. Then, gravity came into play. Areas where there was slightly more dark matter than average began to attract even more matter from the surrounding space, becoming denser over time. This process, known as gravitational instability, worked like a snowball. Over billions of years, these initially tiny condensations grew into giant halos of dark matter, which became gravitational centers for the formation of galaxies and clusters. And what happened to areas where there was initially slightly less dark matter than average? They, on the contrary, lost matter, which flowed into denser regions. These areas became more and more sparse. This is how cosmic voids were born. Voids are, in essence, places from which dark matter was gravitationally evacuated during the formation of the universe, leaving behind only a cosmic desert populated by a very small amount of ordinary and dark matter. Thus, the architecture of space that we observe today is a direct consequence of the initial distribution of dark matter and its subsequent evolution under the influence of gravity. Understanding this process is critically important because it shows that voids are not just holes, but fundamental and integral elements of the cosmological model. And it is in these deserts, where the gravity of dark matter weakens, that the main and most mysterious player, dark energy, enters the scene. If dark matter is the architect of the universe, then dark energy is its engine, and an engine that runs on acceleration. It is the most mysterious force in nature. We don't know what it is, but we can see its effect. It causes the universe to expand faster and faster. Unlike matter, both dark and ordinary, which clumps together under the influence of gravity, dark energy appears to be evenly distributed throughout space. Its density is constant and does not decrease as the universe expands. This property makes it unique. Throughout the universe, there is a constant struggle between two titans: gravity, which tries to compress everything, and dark energy, which tries to push everything apart. In dense areas of space, such as galaxies and clusters, the density of matter is high, and gravity wins out. The Veronica's hair cluster is not expanding, it is gravitationally bound. But in cosmic voids, the picture is completely different. In these deserts, the density of ordinary and dark matter drops to extremely low values. And the density of dark energy, as we remember, remains the same. As a result, it is in the voids that the balance of forces shifts dramatically. Gravity becomes so weak that it can no longer resist the pushing action of dark energy. Voids are its realm. They are natural laboratories where we can observe dark energy in its pure, unadulterated form, where its dominance is absolute. And what dark energy does to voids is not just a local effect. It is a rehearsal for the final act in a long play about the fate of our universe. By observing voids, we are essentially looking into the distant future of the entire cosmos. Because as the universe continues to expand, the average density of matter in it will fall, but the density of dark energy will not. This means that over time, the entire universe will become like one giant cosmic void, where dark energy will reign supreme. The dominance of dark energy in cosmic voids is not a static fact, but the beginning of a dynamic and irreversible process. Under its constant pressure, Voids do not simply expand along with the universe, they grow like bubbles in boiling water, actively absorbing the structures around them. To understand this mechanism, we need to remember the struggle between forces. In dense filaments and clusters, the gravity of matter is still strong enough to resist cosmic expansion. It acts like glue, holding galaxies together. But inside the void, there is virtually no glue. Therefore, the repulsive action of dark energy is not restrained by anything here. As a result, the space inside the void expands slightly faster than the average for the universe. This seemingly insignificant effect has enormous consequences over time. The voids begin to swell from within, putting pressure on the surrounding walls of galaxies. They literally push the filaments apart, causing them to become thinner and longer. Galaxies at the edge of the void experience this additional acceleration, being carried away faster and faster. This is an active process of capture. Voids behave like aggressive formations that devour the cosmic web, increasing their share in the total volume of the universe. This process has already been confirmed by observations. Astronomers studying the motion of galaxies at the boundaries of voids see precisely this picture: an accelerated outflow that cannot be explained by gravitational influence alone. This is a direct manifestation of dark energy in action. By observing this process, we are looking into the distant future. As the universe continues to expand, its average density of matter will steadily decline, and the density of dark energy, as we believe, will remain constant. This means that over time, gravity will lose the battle for larger and larger areas of space. Conditions that are currently characteristic only of voids will become the norm for the entire universe. Thus, voids are not just exotic objects. They are a window into the future. They are a demonstration of the ultimate fate of our cosmos, a future where everything will be subject to the total and eternal domination of dark energy. A future of total and eternal emptiness. This future, predicted by the voids, is both majestic and terrifying. If dark energy really is a cosmological constant, then the process of accelerated expansion is irreversible. In 100 billion years, the universe will be unrecognizable. By that time, the acceleration will be so strong that all galaxy clusters not connected to us by gravity will fly beyond our cosmological horizon. This means that light from them, even if emitted at that moment, will never be able to reach us. The night sky will become almost completely black for our distant descendants. The Andromeda galaxy will collide with the Milky Way, forming a giant elliptical galaxy called Milkomeda. Together with the remnants of the local group, it will become the only visible island of matter in the entire observable universe. Future astronomers, pointing their telescopes at the sky, will see nothing but the stars of their home megagalaxy. They will not be able to detect the dispersion of other galaxies because there will simply be no other galaxies in their field of view. They will not be able to measure the Hubble constant. Moreover, the relic radiation itself, the echo of the Big Bang, will by that time have stretched so much that its wavelength will exceed the size of the observable universe, making it completely undetectable. Future civilizations will be locked in their local group, with no observational data to conclude that the universe once began with the Big Bang and has been expanding ever since. They will most likely develop models of a stationary, eternal, and empty island universe, similar to those that were popular before Edwin Hubble. The entire cosmological revolution of the 20th century, all our knowledge about the origin and evolution of the world, will be inaccessible to them. We live in a very short, privileged moment in cosmic history. The cosmological present, when the universe is still young enough to retain traces of its birth, and old enough to have grown complex structures, including us, capable of reading those traces. This existential conclusion is one of the most profound consequences of the discovery of dark energy, and voids are its most vivid harbingers. But before the universe finally plunges into this informational darkness, voids serve as unique and invaluable scientific tools for studying it. In addition to studying galaxies, we have another completely independent way to see cosmic voids. It involves studying the smallest details of the oldest light in the universe, relic radiation. As we remember, the CMB map is a snapshot of the universe at the age of 380,000 years. But during the 13.8 billion years that this light traveled to us, it did not move in a straight line through absolutely empty space. Its photons crossed the entire large-scale structure that had formed during this time. They fell into the gravitational wells of clusters and climbed the gravitational hills of voids. This process leaves a tiny but measurable trace on light, known as the integrated Sachs-Wolf effect, ISW. Here's how it works for voids. Imagine a photon as a ball rolling down a slope. When a photon enters a void, it essentially climbs a gravitational hill. It spends some of its energy doing this, and its wavelength increases slightly. It redden. Then, as it crosses the vacuum, it begins to descend the hill on the other side, having to regain all the energy it spent. In a static, non-expanding universe, it would regain exactly as much energy as it spent, and there would be no net effect. But we live in a universe where expansion is accelerated by dark energy, and that changes everything. While the photon is flying through the void itself, under the influence of dark energy, manages to expand slightly and become smaller. The gravitational hill becomes flatter. As a result, descending a now gentler slope, the photon receives less energy back than it expended on the ascent. The end result, the photon emerges from the void with a slight energy deficit. It becomes slightly colder than it was before encountering the void. This effect is incredibly small, with the temperature changing by microkelvins. But when astronomers take maps of known nearby voids obtained from galaxy surveys and superimpose them on a map of the cosmic microwave background, they see exactly what the theory predicts. In the directions of the voids, the cosmic microwave background is on average slightly colder. These cold spots are yet another independent, irrefutable proof of the existence of voids, obtained not by counting what is not there, galaxies, but by studying what is there, the oldest light in the universe. The study of these cold spots on the relic background led to the discovery of an even stranger and more anomalous structure than our KBC Void. We are talking about the so-called CMB cold spot and the associated Eridanus supervoid. In 2004, while analyzing data from the WMAP satellite, astronomers discovered an area of abnormally low temperature on the map of relic radiation. This spot, located in the constellation Eridanus, has a diameter of about 5 degrees in the sky, 10 times larger than the diameter of the full moon, and is significantly colder than predicted by standard models of random quantum fluctuations. The probability of such a large and cold spot appearing by chance is estimated to be only 1 to 2%. This is one of the most serious anomalies in the standard cosmological model. Immediately, a hypothesis arose that perhaps this spot is not a feature of the early universe, but a trace of a giant supervoid located between us and the surface of last scattering, which cooled the light through the Sachs-Wolf effect. Subsequent surveys of galaxies in this direction confirmed that one of the largest known voids, the Eridanus supervoid, is indeed located there. Its diameter is estimated to be approximately 1.8 billion light-years, which is comparable to the KBC, and it is located about 3 billion light-years away from us. On the one hand, this discovery was a triumph for the theory. Here is the anomaly, and here is its physical explanation. But on the other hand, it only exacerbated the problem. First, calculations showed that even such a gigantic void can explain only 10 to 20% of the observed temperature of the cold spot. The rest still remains an anomalous fluctuation from the early universe. Secondly, and most importantly, we now have two colossal, statistically improbable supervoids in the observable universe, our KBC and the Eridanus void. If one such event is just bad luck, then two is already a pattern. This suggests that we fundamentally do not understand something about the formation of the largest structures. perhaps the standard model systematically underestimates the probability of such giant holes appearing in the cosmic web. And if this is the case, then the hypothesis that we live in one of them becomes not so exotic, but much more plausible. But let's return to our main crime, Hubble's tension. We have established that the KBC vacuum hypothesis can explain it elegantly. However, if we assume for a moment that this hypothesis is incorrect, and that the local measurement of 73 km/PC reflects the true global expansion rate of the universe, we immediately encounter an even deeper and more insoluble paradox. This is the age problem. The age of the universe is closely related to its expansion rate. The faster it expands, the less time it took to reach its current size. A simple extrapolation back in time based on the Hubble Constant gives us the approximate age of the cosmos. If we use the value obtained from relic radiation, 67, the age of the universe is 13.8 billion years. But if we take the local value of 73 as a basis, the age of the universe is catastrophically reduced to approximately 12.7 billion years. It becomes a whole billion years younger. And here our detective story turns into a logical nightmare, because we have completely independent and very reliable ways to measure the age of the oldest objects in our own galaxy. First of all, these are globular star clusters. These are ancient dense conglomerates of hundreds of thousands of stars that were born at almost the same time. Astronomers can determine their age by studying which stars in them have already evolved and left the main sequence, the stage of hydrogen burning. This method, based on the well-proven theory of stellar evolution, gives an unambiguous result. The oldest globular clusters are between 12.5 and 13.5 billion years old. Now put these two facts side by side. If the universe is 12.7 billion years old, what about stars that are 13.5 billion years old? You can't have stars that are older than the universe itself. This is an absolute glaring paradox. It's like finding a sealed scroll in an ancient tomb that, according to radiocarbon analysis, was made 500 years after the tomb itself was built. One of our key measurements, either the age of the oldest stars or the rate of expansion of the cosmos, is catastrophically wrong. And since the theory of stellar evolution has been tested in many ways, most scientists trust the age of stars. This makes the hypothesis of a rapid global expansion rate even less likely, and forces us to return to our prime suspect. And here, the KBC vacuum hypothesis comes into its own. Not only does it offer a solution to Hubble's problem, but it also elegantly resolves the seemingly unsolvable age paradox. If the hypothesis is correct, then the rapid expansion at a speed of 73 km/MPC is only a local effect observed within our Hubble Bubble. Globally, on average, the universe is expanding at a slower speed, predicted by relic radiation data of 67 km/MPC. It is the global expansion rate throughout the history of the cosmos that determines its age. Thus, the age of the universe remains the same, equal to 13.8 billion years. In this case, there are no problems with stars that are 13.5 billion years old. They fit perfectly into this timescale, leaving even several hundred million years for the formation of the first galaxies. The paradox simply disappears. The vacuum hypothesis acts as a universal key that fits two locked doors at once: Hubble's tension and the age problem. This makes it extremely attractive from a scientific point of view. In science, when a single hypothesis can coherently explain several seemingly unrelated anomalies at once, its value increases many times over. This is a sign that it most likely points to something real. Instead of introducing two different types of new physics, one to explain the anomalous expansion rate, and another to revise the theory of stellar evolution, we get one simple, albeit philosophically uncomfortable, explanation for both problems. And this explanation does not require us to change a single equation in general relativity or in the standard model of particle physics. It only requires us to recognize that the cosmological principle is not an immutable dogma, but a working approximation that can be violated on a sufficiently large scale. And the KBC Void is the scale at which this violation becomes apparent and measurable. This makes the void hypothesis an even more compelling candidate for the true culprit of the cosmological crisis. But are there other independent ways to verify whether we really live in an anomalous zone? Such a method exists, and it is considered one of the most reliable tools in the arsenal of modern cosmology. We are talking about the so-called Baryon acoustic oscillations, or BAO. This is another witness in our case, which gives evidence without relying on supernovae or Cepheids. BAO is, in essence, a standard ruler imprinted in the very fabric of the universe. To understand what this is, we need to go back to the early universe, to the first 380,000 years after the Big Bang. At that time, the universe was a hot, dense plasma consisting of protons, electrons, and photons, as well as dark matter. Sound waves, similar to the circles on water caused by a thrown stone, constantly arose and propagated in this plasma. These waves were areas of increased density that expanded at the speed of sound. They carried baryonic matter, protons, and electrons with them, but not dark matter, which did not interact with photons and remained at the center of the disturbance. When the universe cooled enough for protons and electrons to combine into hydrogen atoms, a process called recombination, the plasma became transparent. The photons broke free, forming relic radiation. At that moment, the sound waves froze. The distance they had traveled by at that point was strictly determined by plasma physics and amounted to about 490 million light-years in modern units. As a result, a characteristic imprint remained in the distribution of matter in the universe, a small excess probability of finding one galaxy at a distance of 490 million light-years from another. This scale, this cosmic ruler, is universal. We can measure the angular size of this ruler in the sky at different distances from us. By comparing the apparent size of this standard ruler with its true size, we can accurately determine how the universe expanded in different eras. So measurements using BAO give a dual result. At large distances, they are fully consistent with Planck data and predict a slow expansion of 67 kilometers at MPC. But in the nearby universe, in the same range where supernovae operate, the BAO method indicates a faster expansion, consistent with 73. It is as if an independent expert, using his own, absolutely reliable measuring instrument, confirmed the testimony of the first witness. This makes the accusation against the standard model even more compelling, and, at the same time, strengthens the position of the void hypothesis. After all, it is this hypothesis that predicts that in our local region of the universe, standard rulers should look different due to our own motion and the distortion of space. Taking all this evidence into account, the discrepancy in H0, the age problem, anomalous flows, and BAO data, it seems that the local void hypothesis is the main and most likely explanation. But the scientific process requires that all alternatives be considered. What if the problem is not really with our location, but with gravity itself? What if Einstein's theory, general relativity, which works flawlessly on the scale of the solar system and even galaxies, fails on the largest cosmological scales? This idea, known as modified gravity, has its supporters. The most famous of these theories is MOND, modified Newtonian dynamics, proposed back in the 980s by Mordecai Milgram to explain the abnormally fast rotation of galaxies without invoking dark matter. MOND suggests that at very low accelerations, typical of the outskirts of galaxies, gravity becomes stronger than Newton's law predicts. Although MOND in its original form has many problems with cosmology, the idea that gravity can behave differently on large scales continues to evolve. Modern theories of modified gravity are much more complex. They suggest the existence of additional fields or even additional dimensions of space that come into play at cosmological distances. How can this solve our problems? It's very simple. If gravity in the past was slightly stronger than we think, or worked differently, then the process of structure formation, that very gravitational instability, would have been much more efficient. This would naturally lead to the formation of richer superclusters and, most importantly, larger and deeper voids. Within some models of modified gravity, the appearance of a void the size of the KBC becomes not a statistical miracle, but a fairly common event. Thus, these theories also offer a solution to the problem, but from a different angle. They preserve the cosmological principle, the idea that our place is unremarkable, but at the cost of abandoning Einstein's standard theory of gravity, which has been tested in thousands of experiments. This is a very high price to pay. It's like trying to explain why the plumbing in one house doesn't work by assuming that the laws of hydrodynamics are different in that city, instead of simply checking whether the house is located on top of a hill. So we stand at the main fork in modern cosmology, at the point where a decision is made about the future of our entire worldview. The road splits, and both paths lead to revolution, but to revolutions of different kinds. The first path, we accept the KBC vacuum hypothesis. We acknowledge that our position in the universe is anomalous, that we live inside a statistically improbable structure that distorts our observations. In this case, we save all the physics we know. Einstein's general theory of relativity remains unshakable. The standard model of particle physics remains valid. We do not need to introduce any new entities, fields, or dimensions. The price we pay is the abandonment of the strict cosmological principle. We will have to accept that we are special observers and always make corrections for our cosmic geography. This is a revolution in the philosophy of science, in our worldview. The second path, we reject the vacuum hypothesis, insisting that our location is unremarkable and that the cosmological principle must be upheld. In this case, we save our philosophical stance, but we have to sacrifice physics. We will have to admit that the general theory of relativity is incomplete or incorrect on a large scale. We will have to create a new theory of gravity that would explain Hubble's tension, the existence of giant voids, and anomalous flows, while preserving all the successes of Einstein's theory on a small scale. This is a revolution in physics itself, in our most fundamental laws of nature. There seems to be no third way that would allow us to preserve both the old physics and the old philosophy. Cosmology has been driven into a corner, and there is no simple, painless way out. Each new piece of observational evidence, each new survey of galaxies, each refinement of the Hubble Constant is a weight that falls on one of these two sides of the scale. And until the scientific community reaches a consensus on which path to choose, this makes our time one of the most exciting in the history of astronomy. We are witnesses to and participants in a shift in scientific paradigm, the outcome of which is still undecided. While theoretical physicists argue about fundamental laws, observational astronomers continue to study the inhabitants of these strange cosmic deserts, galaxies and voids, and this research reveals yet another facet of how much our environment determines our fate. Galaxies born in voids are true cosmic hermits. They evolve in almost complete isolation, while their sisters in dense clusters live in noisy, crowded megacities. And this difference in lifestyle has a dramatic effect on their appearance and properties. First, galaxies in voids are on average smaller and dimmer. Collisions and mergers, which are the main mechanism of galaxy growth in dense clusters, occur less frequently in them. Without this influx of fresh material, they remain small. Second, they are much bluer. In astronomy, blue color is a sign of active star formation and the presence of young, hot stars. In clusters, frequent interactions and hot intergalactic gas quickly deprive galaxies of their cold gas reserves, stopping star formation and turning them into red and dead elliptical systems. In voids, however, galaxies retain their gas reserves for billions of years, continuing to slowly but surely form new generations of stars. Therefore, spiral and irregular galaxies rich in gas predominate among them. By studying them, we are looking at a nature reserve of the early universe. These galaxies are living fossils that show us what most galaxies would look like if they had not gone through the meat grinder of gravitational interactions in clusters. They are an ideal laboratory for studying the pure evolution of galaxies, uncontaminated by the influence of their surroundings. This allows scientists to better understand which processes are internal to galaxies and which are imposed on them from outside. Even our own galaxy, located on the edge of the void, bears the mark of this duality. It is large enough, but still has active star formation, unlike the giant elliptical monsters at the centers of clusters. When studying our local environment, we encounter a striking paradox of scale that once again highlights the grandeur of the KBC Void. Our own cosmic home, a structure we consider gigantic, is the Laniakea supercluster. This term was introduced in 2014 by a group of astronomers led by Brent Tully, and translated from Hawaiian, it means vast heavens. And this name is well deserved. Laniakea is a colossal structure, more than 520 million light-years across, containing about 100,000 galaxies, including our Milky Way. All these galaxies are gravitationally bound. They do not move chaotically but flow, like rivers in one large catchment basin, towards a common center of mass, the Great Attractor. Laniakea is one of the largest structures in the known universe, and now, a paradox. This entire immense structure, our home to 100,000 galaxies, is entirely located within the KBC Void. It's like discovering that the huge continent you thought was the main part of the world is actually just one of the islands in a much larger and almost empty ocean. How is this possible? The answer lies in the definition of density. The KBC Void is characterized as an area with a lower average density, on a scale of billions of light years. But that doesn't mean it's completely empty. Inside it, as everywhere else in the universe, there is its own local structure. Laniakea and other clusters like it are the very rare oases of matter in this gigantic cosmic desert. Their total mass is not enough to compensate for the overall density deficit in this huge volume. This fact clearly demonstrates how prone we are to errors in perceiving scale. We consider a supercluster of galaxies to be something incredibly large because it exceeds anything we can imagine. But in the context of the entire universe, even such a structure may turn out to be only a minor fluctuation within a much more grandiose formation. In this case, a formation with a minus sign. This realization forces us to reconsider our place once again. We do not live in a vacuum. We live in one of its densest regions, in a metropolitan oasis, in the middle of a universal desert. And even from here, from this oasis, the influence of the surrounding desert is felt in the most immediate way. This influence manifests itself not only in our own motion, but also in the coordinated motion of huge groups of galaxies. This phenomenon is known as bulk flows. As we remember, the cosmological principle assumes that the universe is homogeneous on a large scale. This means that gravitational forces must be balanced, and there should be no preferred directions for motion. The peculiar velocities of individual galaxies should be chaotic and, on average, compensate for each other. If we take a sufficiently large cube of space, say 500 million light-years across, then the average velocity of all galaxies within it should be close to zero. However, observations show a completely different picture. Numerous studies, such as the Cosmic Flows Project, which has been mapping the velocities of thousands of galaxies for decades, have found that vast regions of space move as a single entity. This is not chaotic motion, but a coherent flow, a cosmic river in which entire superclusters rush in one direction at speeds of hundreds of kilometers per second. These flows are too fast and too large in scale to be explained within the standard LCDM model, assuming that the universe is homogeneous on average. In simulations, such large-scale and fast flows are extremely rare, but they are a natural and inevitable consequence of the existence of a giant anomaly, such as the KBC Void. Recall our analogy with a gravitational hill. All the material at the top and on the slopes of this hill will flow down into the surrounding valleys. This is a volumetric flow. Models that include the KBC Void predict the existence of precisely such flows, with observed speeds and directions. Matter inside the void accelerates outward, toward dense structures beyond its boundaries. These cosmic rivers are the most direct and obvious evidence of the gravitational imbalance created by the void. We are not simply deducing its existence from theoretical models. We can literally see matter leaving empty regions and rushing into dense ones. For our investigation, this is another crucial piece of evidence. Anomalous flows, which are a problem for the standard homogeneous model, become confirmation for the model in which we live inside a giant void. This is another example of how the void hypothesis turns an anomaly into a prediction. All these lines of evidence, the local value of H0, the age problem, the existence of KBC and Eridanus, anomalous streams, come together to form a single, consistent picture. This picture is described by a concept called the Hubble Bubble. This idea suggests that we live inside a giant low-density bubble, and all our local cosmological measurements are systematically distorted by this fact. Inside this bubble, due to gravitational outflow, we measure a higher value for the Hubble Constant. But outside it, in the normal, average universe, the expansion rate is lower and corresponds to the value obtained from relic radiation data. This hypothesis makes one very clear and testable prediction. If it is correct, then the measured value of the Hubble constant should depend on distance. For the closest objects, inside the bubble, it should be high, around 73. As we look at increasingly distant objects, approaching the edge of the bubble and going beyond it, the measured value of H0 should gradually decrease, asymptotically approaching the global value of 67. And most strikingly, the latest observational data are beginning to hint at just such a trend. Several independent studies analyzing supernovae at different distances have shown that for the closest sample of supernovae, H0 is indeed higher, and for the more distant ones, it is lower, closer to the Planck value. These results do not yet have sufficient statistical significance to be considered definitive proof, but they are a strong argument in favor of the Hubble Bubble hypothesis. If this trend is confirmed, it will be a near knockout blow to the idea of new physics and a triumph for the geographical explanation. This means that we are literally locked in a bubble of distorted space-time. Our most reliable, most accurate instruments for measuring the nearby universe are failing not because they are inaccurate, but because we are using them inside a laughing room, where all rulers appear shorter and all speeds appear faster. And the only way to see the real picture is to learn to see through the walls of this room. This is precisely what astronomers will be doing in the coming decade, attempting to see through the walls of our local bubble. We are on the threshold of a new era in observational cosmology, an era of mega surveys that will allow us to map the universe in 3 dimensions with unprecedented accuracy and at previously unattainable distances. 2 key instruments in this work are the Euclid Space Telescope, launched by the European Space Agency, and the Vera C. Rubin Observatory in Chile. Their task is to measure the positions, distances, and shapes of billions of galaxies, looking far beyond the supposed boundary of the KBC Void. Euclid will use 2 main methods. First, it will measure baryon acoustic oscillations over vast distances, tracking how our standard ruler changes over cosmic time. This will allow us to construct a highly accurate distance scale and verify whether the measured value of H0 actually decreases with distance. Second, it will study the effect of weak gravitational lensing, microscopic distortions in the shape of distant galaxies caused by the gravity of dark matter in the foreground. This will allow us to map the distribution of invisible dark matter and see directly whether our void is part of a larger structure. The Vera Rubin Observatory, in turn, will conduct a 10-year survey of the entire southern sky, discovering millions of new supernovae at different distances. This will allow us to increase the statistics many times over and verify with high accuracy whether H0 depends on distance. This future data will provide a definitive answer to many questions in our investigation. They will either clearly show that outside our bubble, the expansion rate is indeed lower, and then the void hypothesis will be confirmed. Or they will show that Hubble's tension persists at large distances, and then we will have to seriously consider options with new physics, It's like building a ship to finally sail beyond the confines of our familiar, well-studied, but possibly anomalous harbour, and see if the world beyond it is really different. The answer that these missions will bring will determine the direction of cosmology for decades to come. So, our detective investigation is coming to its logical conclusion. Let's put all the evidence together. We have a crime scene, a fundamental discrepancy in measurements of the expansion rate of the universe. We have a prime suspect, the giant, statistically anomalous KBC Void, at the center of which we find ourselves. We have a murder weapon, the gravitational outflow that distorts our local measurements. And we have a whole series of independent testimonies confirming the suspect's guilt. The problem of the age of stars, which arises in the hypothesis of rapid global expansion, disappears completely if rapid expansion is only a local effect. Anomalously fast and large-scale volumetric flows of galaxies, which do not fit into the standard homogeneous model, are a direct prediction of the giant void model. Data on baryonic acoustic oscillations, obtained using a completely different technique, confirm that our local universe is indeed expanding faster than the distant one. Finally, the first hints of the existence of the Hubble Bubble, the dependence of h0 on distance, are beginning to appear in supernova data. All these seemingly disparate clues point to the same culprit. The void hypothesis is the most economical, simplest explanation that ties all these facts together without requiring us to invent new physics. It asserts that there is no conspiracy on the part of the universe. There are only the laws of physics operating under the anomalous conditions of our location. To acknowledge this is to overturn our understanding of our own place in the cosmos. It means understanding that we are not just passive observers, but active participants in local dynamics, and we must take these dynamics into account in all our conclusions. This puts an end to our investigation, but opens a new chapter in our understanding of the cosmos. Our investigation is complete, but the story does not end there. We have arrived at a final question that takes us beyond a simple comparison of facts and forces us to consider the nature of scientific knowledge. Which is more likely? That we live in a statistically improbable, unique place that distorts our observations? Or that there is a profound flaw in our most fundamental theories about the universe? The KBC Void hypothesis, as we have shown, elegantly explains many observational paradoxes. But it relies on the assumption of our specialness, which contradicts centuries of scientific tradition. Alternative hypotheses involving new physics preserve our ordinariness, but require a revision of the laws of gravity or the introduction of new invisible components into the universe, for which we currently have no direct evidence. This choice is not simply a choice between two scientific models, it is a choice between two types of probability. On the one hand, there is the extremely low spatial probability of our location. On the other hand, there is the speculative probability that our proven theories are incorrect. Which of these improbabilities is less improbable? The answer to this question will change cosmology forever. If future observations confirm the Hubble Bubble hypothesis, it will be a triumph for classical physics, but it will force us to abandon the naive cosmological principle forever. We will understand that the universe is not a smooth and homogeneous canvas, but rather a patchwork quilt of regions with different local properties, and we happen to live in one of the most unusual patches. If it turns out that Hubble's tension persists beyond our local void, it will mean that the standard cosmological model is indeed incomplete, and a new physical revolution awaits us, comparable to the creation of the theory of relativity or quantum mechanics. The question is no longer whether we are alone in the universe. Now the main question is, do we see this universe as it really is? Or will we forever remain hostages to our local cosmic mirage, trying to decipher universal laws from a distorted reflection? To gain a deeper understanding of the nature of our suspect, we must look back to the very first moments of the universe's existence. Where do such gigantic structures as voids and superclusters come from? Their seeds, their root cause, are hidden in the world of quantum mechanics. According to the theory of cosmological inflation, in the first tiny fraction of a second after the Big Bang, approximately from 1036 to 10 to 32 seconds, the universe experienced a period of exponential superluminal expansion. In that instant, it increased in size an unimaginable number of times. At this moment, virtual particles constantly appeared and disappeared at the subatomic level, a phenomenon called quantum fluctuations. In a normal, non-expanding universe, these fluctuations would have remained microscopic. But inflation worked like a giant cosmic microscope. It stretched these microscopic fluctuations in density and energy to astronomical, macroscopic scales. Areas where, by pure chance, the energy density was slightly above average were stretched and became the seeds of future galaxy clusters. And areas where the energy density was slightly below average became the seeds of future cosmic voids. It's a striking idea. The largest structure in which we live, the KBC Void, is a direct descendant of a random quantum event that occurred in the first moments of time and space. Our place in the universe, our cosmic geography, was predetermined by a subatomic lottery 13.8 billion years ago. This connection between the smallest thing we know, the quantum world, and the largest, the cosmic web, is one of the greatest triumphs of modern cosmology. It shows that the deterministic, predictable structure we see today was born out of fundamentally random, probabilistic chaos. It also means that the map of voids and filaments is, in essence, a magnified photograph of the quantum world at the moment of the universe's birth. By studying these structures, we can test our most daring theories about ultra-high energy physics, which cannot be achieved in any terrestrial accelerator. But how did these barely noticeable, microscopic differences in density, amounting to only 1/100,000th of a percent, give rise to such a contrasting and grandiose structure as the cosmic web? The answer lies in the slow, inexorable, and creative force of gravity. After inflation ended, the universe continued to expand, but at a much slower pace. And then gravity came into play, amplifying the initial inhomogeneities. This process, known as gravitational instability, works on a simple principle that can be described as the rich get richer and the poor get poorer. Areas that were slightly denser than average after inflation began to attract matter, mostly dark matter, from the surrounding space. The more matter they attracted, the stronger their gravity became, and the more effectively they attracted even more matter. This positive feedback cycle, which lasted for billions of years, caused these regions to collapse into dense halos of dark matter, which then became homes for galaxies and clusters. On the other hand, regions that were initially slightly less dense lost out in this gravitational competition. Their rich neighbors actively stole matter from them. As a result, these regions became increasingly empty, turning into giant voids. Thus, the cosmic web is nothing more than the result of billions of years of gravitational sorting, which transformed the nearly homogeneous soup of the early universe into a sharply contrasting structure of extremely dense filaments and extremely empty voids. This passive but almighty process, where gravity simply amplified what was already laid down at the quantum level, is the architect of our cosmic home. Understanding this mechanism once again emphasizes that voids are not some kind of byproduct, but a fundamental, integral part of the overall picture. They are as much a prediction of the standard cosmological model as galaxy clusters are, and that is precisely why their anomalous size poses such a serious problem for this same model. Our intuitive understanding of space is shaped by images from telescopes, clusters of stars, spiral arms of galaxies, nebulae. We think of space as a space filled with objects. But this is a fundamental error of perception, caused by the fact that we live in one of its most overpopulated corners, inside a galaxy. If we look at the universe on a true scale, we will see that galaxies and their clusters are an anomaly. The normal state of the universe is emptiness. As we have already mentioned, voids occupy about 90% of the entire volume of the observable cosmos. All visible and dark matter is concentrated in the remaining 10% of the volume, in thin threads and walls of the cosmic web. This leads to a striking conclusion. We do not live in a universe filled with galaxies, but in a universe of emptiness, where only occasionally, like dust in the sun, do islands of matter appear. This completely changes our perspective. It's as if an alien who flew to Earth made conclusions about its surface by studying only cities and roads, without noticing that 90% of the planet is oceans, deserts, forests, and fields. Galaxies are the cities of the universe, but most of it is wild, uninhabited nature. This realization is important because it forces us to rethink what is normal. Normal is emptiness, extremely low density, the dominance of dark energy, and the almost complete absence of gravitational interactions. And our reality, life inside a dense galaxy, which is inside a relatively dense supercluster, is a profound, multi-level exception to the general rule. Even though we are inside the giant void of the KBC, we are still in its densest part, in the oasis of Laniakea. This fractal nature of our special position makes the cosmological principle even more shaky. Perhaps it works when averaged across the entire universe, but for us, as observers living at a point of multiple anomalies, it may simply be inapplicable in practice. Let's return to the statistical side of the problem and assess how serious it is, using language that physicists understand. In science, especially in particle physics, the so-called 5 sigma criterion is used to claim a discovery. Sigma, SES, is a measure of statistical deviation from the expected result. A 1 sigma deviation is a normal random occurrence. A 3 sigma deviation is a serious anomaly that deserves attention. The probability of a random occurrence is 1 in 370. But 5 sigma is the gold standard. This means that the probability that the observed result is a random fluctuation is less than 1 in 3.5 million. This is the level of confidence that was achieved when the Higgs boson was discovered. And now, to our void. Different groups of researchers using different methods of analysis estimate the statistical anomaly of the existence of the KBC Void in LCDM simulations. And although the estimates vary slightly, many of them indicate that this deviation is between 3 and 5 sigma. This means that we live in a place that, according to our best theory, simply should not have come into being. If such a result had been obtained in an experiment at the Large Hadron Collider, physicists around the world would already be celebrating the discovery of new physics that refutes the standard model. But in cosmology, the reaction is much more restrained. Why? Precisely because of the philosophical discomfort we mentioned earlier. Many scientists prefer to believe that this is simply an incredible statistical coincidence, rather than abandon the cosmological principle. This double standard is an interesting phenomenon in the sociology of science, but it does not negate the fact that the strict statistical criteria applied in one area of physics are, for some reason, not applied with the same rigor in another, when the result affects our fundamental ideas about our place in the universe. This underscores how the KBC vacuum hypothesis is not just a scientific problem, but a real challenge for the entire culture of scientific knowledge. In addition to their influence on cosmological measurements, voids play another important role. They act as a great filter for the formation of structures. In dense regions of the universe, such as filaments and especially galaxy clusters, the evolution of matter is rapid and dramatic. Gravity is so strong here that it easily overcomes the general expansion of space. Galaxies constantly collide and merge with each other, and small galaxies are absorbed by larger ones. This process, called hierarchical clustering, is the main driver of structural growth. As a result, giant elliptical monster galaxies grow in the centers of clusters, dozens of times more massive than our Milky Way. But in voids, this scenario is impossible. The density of matter here is so low that gravity is too weak to start this process of big construction. It is capable of forming separate, small galaxies, but cannot bring them together into large, gravitationally bound groups and clusters. Voids are an environment where gravitational instability, the very principle of the rich get richer, fails due to total poverty. As a result, the evolution of structures in voids seems to freeze at a very early stage. They remain forever in an underdeveloped, primitive state that dense regions of the universe passed through billions of years ago. This filtering effect has direct observational consequences. When astronomers study the most massive and brightest objects in the universe, quasars, rich galaxy clusters, the most powerful radio sources, they find them exclusively in dense filaments and walls of the cosmic web. There are no such objects in the voids. This means that voids are not only areas of low density, but also areas where the formation of the most extreme and interesting objects is physically impossible. They are cosmic back alleys, quiet backwaters where evolution has almost stopped. This, in turn, makes them unique laboratories for studying the past. But we will talk about that a little later. This quiet life of galaxies and voids affects not only their size and shape, but also their chemical composition. In astronomy, all elements heavier than hydrogen and helium are commonly referred to as metals. These elements were not created in the Big Bang. They are produced in the depths of stars during thermonuclear fusion and ejected into interstellar space at the end of a star's life, especially during supernova explosions. Each new generation of stars is formed from gas enriched with metals left over from previous generations. Thus, over time, galaxies gradually become metallic. The rate of this process depends directly on the intensity of star formation and on how effectively the galaxy retains the gas ejected by supernova. In dense clusters, where galaxies often collide, their gas clouds mix, which can cause violent bursts of star formation, quickly enriching the galaxy with metals. On the other hand, interactions can also sweep gas out of the galaxy, carrying away precious heavy elements. In voids, as we know, evolution proceeds much more calmly. Star formation proceeds slowly and monotonously, without sudden bursts. Galaxies effectively retain their gas, as there are no external forces to take it away. As a result, galaxies in voids should have a lower average metallicity than galaxies of the same mass in clusters. Observations generally confirm this trend. But this raises an interesting question related to the possibility of the emergence of life. The formation of Earth-like planets requires heavy elements such as silicon, iron, oxygen, and carbon. From this point of view, the low metallicity of galaxies in voids may be a negative factor. On the other hand, the turbulent life in clusters is also not conducive to the emergence of life. Frequent nearby supernova explosions and powerful radiation from active galactic nuclei can sterilize any nascent life on planets. Voids, on the other hand, offer a much more stable and safe environment over billions of years. So, where are the better conditions for life? In rich but dangerous megacities or in poor but peaceful villages? Perhaps our anomalous location, on the edge of a dense supercluster but inside a giant void, is a kind of golden mean, not only a curse for cosmological measurements, but also a blessing for our own existence. Throughout our investigation, we have used terms such as the universe is lying, cosmic conspiracy, and deception. Of course, these are just metaphors. The universe has no mind or malicious intent. It is not trying to confuse us on purpose. But the laws of physics operating in our anomalous location create an effect that, to us as observers, is equivalent to deception. This is an inevitable physical effect of perspective. Any observer located at the center of any sufficiently large and deep void would come to exactly the same erroneous conclusions about the local expansion rate of the universe. They would also discover Hubble Tension. They would also encounter the problem of the age of stars. Their conclusions about the universe would not be universal laws, but local artifacts. This undermines the very idea of objective reality in cosmology. We are accustomed to thinking that when we point a telescope at the sky, we see reality as it is. But the vacuum hypothesis tells us that we see reality filtered and distorted by our own gravitational environment. It's like looking at the underwater world through a layer of water. The water refracts light. distorting the sizes and positions of objects. We can learn to correct for this distortion, but we will never be able to see the world as if there were no water. Our conspiracy is not malicious intent, but a natural consequence of our unique vantage point. And this has profound implications. It means that in order to properly understand the universe as a whole, we must first perfectly understand our local environment. Cosmology becomes similar to archaeology. Before drawing conclusions about an entire civilization, we must carefully study the cultural layer in which we ourselves are located, and understand how it might have influenced our findings. This makes the task of cosmologists much more difficult, but at the same time, much more interesting. Let's conduct a final and most vivid thought experiment to finally convince ourselves of the power of the vacuum hypothesis. Imagine that we have a spaceship capable of instantaneous travel through space. We begin our journey here in the Milky Way and measure the Hubble Constant for nearby supernovae. We get a result of 73. Now we move 2 billion light years to the side, leaving the boundaries of the KBC Void and finding ourselves in an average filament of the cosmic web. We take the same measurements again, on the same set of supernovae. What result will we get? According to the Void hypothesis, we will get 67. The paradox will disappear, simply because we have changed our point of observation. Looking back towards our home, we would see something remarkable. We would see that the galaxies within the region where we just were are indeed flying apart faster than the average for the universe. We would see the same volumetric flow, the same outflow from the void, but no longer as participants, but as outside observers. It would become absolutely obvious to us that our previous measurement was contaminated by our own movement. The local effect would become apparent. This thought experiment proves that the Hubble crisis is most likely not a problem of physics, but of cosmic geography, our own unique and anomalous geography. Unfortunately, in reality, we cannot make such a leap. We are tied to our observation point, to our ship called the Milky Way, which is rushing along in this gravitational flow. But that is precisely why future surveys such as Euclid are so important. They are, in essence, our only way to make this leap, not physically but virtually, by gathering enough data about distant parts of the universe so that we can compare them with our local environment and draw a final conclusion. This highlights how fragile and context-dependent our knowledge can be. What does the future hold for us? Will we ever leave this void? The answer is no. What's more, our position within it will become increasingly pronounced. The accelerated expansion of the universe caused by dark energy will make our bubble our eternal prison. As we have already discussed, voids expand faster than the average for the universe. This means that even though we are moving at a speed of 600,000 miles per hour, we will never be able to escape from the KBC void. It will expand faster than we can cross it. Our local bubble will eventually become our entire visible reality. In 100 billion years, due to accelerated expansion, all galaxies outside our gravitationally bound local group, which by then will become one giant Milky galaxy, will disappear beyond the cosmological horizon. We will remain in complete isolation. For future inhabitants of our galaxy, the universe will look like a single island of matter in an infinite, dark, and completely empty ocean. They will have no data to measure the expansion of space or learn about the Big Bang. All information about our grand past, about the cosmic web, about relic radiation will be forever erased by accelerating space. Our time is truly a unique era. We live in that brief interval of cosmic history when the universe is old enough for us to appear and build telescopes, but young enough for us to still see traces of our origins. The KBC void in which we live is not just a geographical anomaly. It is a harbinger of the future, a demonstration of what our entire universe will eventually become. We are already living in the future that awaits everyone else. So, our scientific detective story is coming to an end, leaving us at a crossroads, face to face with two powerful but mutually exclusive ideas. All the evidence has been examined, all the witnesses have been questioned. Now it's time to sum up. The first path we explored is that of the local anomaly. It asserts that all the drama we observe, the entire crisis in cosmology, is a consequence of our unique location within the giant KBC Void. This path preserves all the physics we know intact. Einstein's theory of gravity and the Standard Model remain valid. The price of this path is the rejection of the cosmological principle and the recognition that we live in a statistically anomalous, special place. The second path is the path of new physics. It asserts that our location is ordinary and that the problem lies in the laws of nature themselves. This path preserves our philosophical conviction of ordinariness, but requires a radical revision of the most fundamental theories, perhaps even the theory of gravity itself. Our investigation has shown that the first path, the void hypothesis, currently explains more observational facts with fewer new assumptions. It simultaneously solves the Hubble problem, the problem of the age of stars, and explains the anomalous flows of galaxies. It transforms a multitude of disparate anomalies into a single, coherent, and predictable picture. But the final verdict has not yet been reached. It will be delivered by future observations that look beyond our local bubble. Whatever the outcome, one thing is clear. We are living in an era of great scientific revolution. The old, simple, and elegant picture of a homogeneous universe is crumbling before our eyes. It will be replaced either by a universe in which our location matters, or by a universe governed by new laws that we have not yet discovered. Both options are breathtaking, and the KBC Void is at the very epicenter of this looming storm. Now that the main part of our investigation is complete, let's return to some key pieces of evidence and examine them in more detail. Let's start with the measuring sticks for the nearby universe. Cepheids. What are these stars and why are we so confident in their reliability? Cepheids are a class of giant yellow stars that are at a certain unstable stage in their evolution. They pulsate rhythmically, contracting and expanding, which causes their brightness to change periodically. Back in the early 20th century, astronomer Henrietta Leavitt, working with photographic plates of the Magellanic Clouds, made a fundamental discovery. There is a strict relationship between the period of these pulsations and the absolute luminosity of the star. The brighter the Cepheid, the slower it pulsates. This discovery was a real gift for astronomers. It turned Cepheids into standard candles. Imagine that you have a series of identical 100-watt light bulbs placed at different distances. By measuring their apparent dimness, you can accurately calculate the distance to each of them. It's the same with Cepheids. We find a Cepheid in a distant galaxy. We measure its pulsation period, for example, 30 days. Based on the period-luminosity relationship, we know what its true absolute brightness should be. Then, we measure its apparent brightness with our telescope. By comparing these two values, we can calculate the distance to the galaxy in which it is located with high accuracy. It was this method that Edwin Hubble used in the 1920s to prove that the Andromeda Nebula is a separate galaxy and not part of the Milky Way, and to measure the expansion of the universe for the first time. Today, thanks to the Hubble Space Telescope, we can observe Cepheids in galaxies up to 100 million light-years away. Of course, the method has its complications. It is necessary to calibrate the period-luminosity relationship very accurately by measuring the distance to the nearest Cepheids using geometric methods such as parallax. The absorption of light by interstellar dust must be taken into account. But over decades of work, astronomers have learned to cope with these difficulties, and today, Cepheids remain one of the most reliable pillars in constructing a scale of cosmic distances. But Cepheids, despite their reliability, are not bright enough to be seen at cosmologically significant distances, where the expansion of the universe becomes the dominant effect. To see further, astronomers need a more powerful light bulb, and that light bulb is a type Ia supernova. These events are among the most powerful explosions in the universe. They are so bright that they can outshine their entire parent galaxy for several weeks. Most importantly, they are remarkably uniform. Type Ia supernovae are believed to be the result of a thermonuclear explosion of a white dwarf, the dense remnant of a star like our Sun. The explosion occurs in a binary system when the white dwarf steals matter from its companion. When its mass reaches a critical limit known as the Chandrasekhar limit, about 1.44 times the mass of the Sun, it becomes unstable and explodes. Since the mass at the moment of explosion is always approximately the same, and the physics of the explosion is also standard, the amount of energy released, and therefore the peak absolute luminosity, is always practically the same. This makes them ideal standard candles for the distant universe. Astronomers construct a so-called cosmic distance ladder. First, they calibrate the distances to nearby galaxies using Cepheids. Then, in some of these same galaxies, they observe Type Ia supernova explosions. Knowing the distance to the galaxy from the Cepheids, they can accurately determine the absolute luminosity of these supernovas. They then use this calibrated luminosity as a reference for measuring distances to much more distant galaxies, where Cepheids are no longer visible. It was observations of distant Type Ia supernovae in the late 1990s that led to the revolutionary discovery of the accelerated expansion of the universe and the existence of dark energy. Today, this method allows us to measure distances of billions of light years, precisely in the range that is important for determining the Hubble constant. It is on these two pillars, Cepheids and supernovae, that the local measurement of H0 rests, giving a result of 73. And what lies at the heart of the second competing dimension, which gives a result of 67? Here we turn to a completely different era and a completely different physics. We look at a map of relic radiation, or CMB, the oldest light in the universe. This map is not just a pretty picture, it is a treasure trove of cosmological information. It shows us the universe at the age of 380,000 years, when it was dense and hot. We see tiny temperature fluctuations on this map, areas that were 100,000th of a degree hotter or colder than average. These hot and cold spots have a characteristic size in the sky. The most pronounced size of these spots is about 1 degree, and this size is not accidental. It corresponds to the very distance that sound waves managed to travel in the plasma of the early universe before recombination, our standard ruler of the BAO. We know the physics of the early universe with incredible accuracy. Therefore, we can calculate what the physical size of this ruler was at that moment, and we can see what angular size it has in the sky today. Knowing its true size and its apparent angular size, as well as the distance that light has traveled from it, 13.8 billion years, we can use simple geometry to calculate the entire history of the expansion of the universe between that moment and today. This calculation includes all the key parameters: the density of dark matter, the density of ordinary matter, the density of dark energy, and of course, the expansion rate today, the Hubble constant. Analysis of the angular power spectrum of CMB fluctuations, i.e. the relative strength of spots of different sizes, allows us to determine all these parameters with an accuracy of a few percent. This is the most accurate and reliable source of data in cosmology, and it is this analysis, carried out by the Planck satellite, that gives us a value of H0 equal to 67.4 plus 0.5 km/MPC. It is important to understand that this is not a direct measurement of the current expansion rate. It is a prediction based on data from the early universe and our standard model. And the fact that this prediction does not match direct measurements is the essence of the crisis. It is a clash of two worlds: the cosmology of the early universe and the astrophysics of the nearby universe. Let's return once more to the most complex but most important idea of our investigation: the mechanism of gravitational outflow. We use the analogy of a hill and a valley, which is very useful for intuitive understanding. But now let's add more physical details to reinforce this concept. Imagine an idealized void, a perfectly spherical region of reduced density surrounded by a perfectly homogeneous universe. Where is the center of mass of this system? It simply does not exist in the traditional sense, but we can talk about gravitational potential. Inside the void, due to the lack of mass, the gravitational potential will be higher less negative, than outside. Gravity always causes objects to move from an area of higher potential to an area of lower potential. It's like a ball that always rolls down a mountain, high potential, into a valley, low potential. Thus, any test particle or galaxy inside this sphere will experience a force directed from the center outward, toward denser areas. Now, let's make the model more realistic. The void is not in a vacuum. It is surrounded by walls and filaments where the density is higher than average. These structures create deep valleys of gravitational potential around the hill of the void. The force acting on a galaxy inside the void will depend on its position. If the galaxy is located exactly in the center of a perfectly symmetrical void surrounded by perfectly symmetrical walls, the total force acting on it will be zero. But if it shifts even slightly from the center, the attraction of the nearest wall will become stronger, and it will begin to accelerate in its direction. Measurements show that our Milky Way is not located in the very center of the KBC Void, but is shifted away from it. And we are not in a perfectly symmetrical environment. Around us are the Great Attractor, the Shapley supercluster, and other massive structures. Therefore, we are affected by the resulting gravitational force, which pushes us out of the void. This is not some mystical anti-gravity. It is ordinary, good old Newtonian or Einsteinian gravity, but under conditions of complex, asymmetrical mass distribution. And it is precisely this complexity that modern cosmology must take into account before drawing conclusions about the global properties of the universe. Armed with all these details, let's take another look at the essence of the crisis. Why is the difference between 67 and 73 not just a slight discrepancy, but a real chasm for cosmology? The fact is that the Hubble Constant is not just some number. It is one of the three fundamental parameters describing our universe within the Standard Model, along with the density of matter and the density of dark energy. By changing one of them, you upset the delicate balance that makes the whole model work. The LCDM model, calibrated using data from cosmic microwave background radiation, gives us a very accurate recipe for our universe: approximately 5% ordinary matter, 27% dark matter, and 68% dark energy. And for this recipe, the only possible value of H0 today is 67. If we force the value 73 into this model, the whole picture of the early universe will no longer fit together. The size of the acoustic horizon at the moment of recombination will change, and the predicted spectrum of fluctuations in the cosmic microwave background will no longer match what we observe with incredible accuracy. It's like trying to bake a cake using a proven recipe, but arbitrarily increasing the oven temperature by 10%. Most likely, you will end up with something burnt and inedible. To save the model at H073, we will have to start changing other ingredients. For example, we can assume that dark energy in the early universe behaved differently than it does today, so-called early dark energy. Or that there were some additional relativistic particles, dark radiation. Or that dark matter interacts with other particles. All these hypotheses are the very new physics. Each of them solves Hubble's problem, but creates new problems and requires its own evidence, which we do not have. That is why the difference between 67 and 73 is so important. It shows that either our recipe for the universe is fundamentally wrong, or we are baking our cake in a very strange, non-standard oven. The vacuum hypothesis is precisely a hypothesis about a non-standard oven. It says that the global recipe for the universe is most likely correct, and H067, but our local baking conditions introduce a systematic error into our temperature measurements. Now let's do a final recap. Looking at the big picture like a detective wrapping up a case, we've got 4 separate puzzles, at least at first glance. Puzzle 1. Hubble Tension. Why do the two most accurate ways to measure the expansion rate give different results? Mystery 2. The age problem. Why is the age of the universe, calculated from the local expansion rate, less than the age of the oldest stars? Mystery 3. Anomalous flows. Why are huge areas of the universe moving too fast and too consistently, contrary to the predictions of the homogeneous model? Riddle 4. Statistical anomaly. Why do we live in the center of a giant void, the probability of which occurring by chance is negligible? If we try to solve these riddles separately, we will have to invent 4 different, unrelated hypotheses. For Hubble tension, we would need new physics for dark energy. For the age problem, we would need to revise the theory of stellar evolution. For anomalous flows, we would need to assume very rare initial fluctuations. For the statistical anomaly, we would simply have to accept that we are incredibly lucky. But the KBC vacuum hypothesis offers us something much more powerful. It offers a single solution to the first 3 puzzles and turns the 4th from a problem into the solution itself. Let's take a look. If we accept the void hypothesis, statistical anomaly, then Hubble tension is immediately explained as an artifact of our motion. The age problem disappears, as the global age of the universe remains the same, and anomalous flows become not an anomaly, but a direct and inevitable consequence of gravitational outflow from this void. 1 hypothesis, 3 problems solved. The 4th problem becomes the key to all the others. This is what science calls the heuristic power of a theory, its ability to explain and connect a wide range of phenomena. That is why, despite philosophical discomfort, the void hypothesis remains such a serious and respected candidate for explaining the cosmological crisis. It brings order to the chaos of observational data. Let's delve a little deeper into the visualization of simulations. How exactly is the universe born on a computer screen? It all starts with a box, a 3-dimensional cubic space that will represent a section of the virtual universe. Programmers put the ingredients into this box according to the recipe of the LCDM model. A certain amount of dark matter, baryonic matter, and establish the laws by which they will interact. Gravity, and by which space itself will expand, under the influence of dark energy. Then, tiny random density fluctuations are introduced into this almost homogeneous mixture, which mimic the very quantum ripples left over from inflation. And then, time starts. The supercomputer begins to calculate step by step how each of the billions of elements of matter in this box will evolve. We see gravity begin its work. Areas that were slightly denser are pulled together into small clumps, the first halos of dark matter. Over time, these small halos merge with each other, forming larger and larger structures. Matter begins to form into thin filaments that stretch between the most massive clumps. On the computer screen, over the course of virtual billions of years, a cosmic web grows before our eyes. This is one of the most beautiful and mesmerizing results of modern computational astrophysics. These simulations, such as the Millennium Simulation or the more modern Illustras and TNG, reproduce the observed structure of the universe with striking accuracy. The number of galaxies of different masses, their distribution in space, their colors and shapes. But when we begin to analyze the empty space in these simulations, we encounter that very problem. There are voids in them, many of them. But there are almost no voids the size of KBC. The computer, following the laws of the standard model programmed into it, simply does not want to create such gigantic anomalies. This is visual, clear confirmation that our environment is a statistical outlier. We have talked a lot about galaxies and voids as a reserve of the early universe. Let's explore this idea in more detail. What exactly makes them so special? Imagine 2 seeds from the same plant. You plant one in fertile soil in a dense, competitive forest, where it has to compete with other trees for light and resources. The other you plant in poor soil in an open field where it has no competitors. Obviously, 2 completely different plants will grow. The same is true for galaxies. A galaxy that finds itself in a dense cluster, forest, is constantly subjected to external influences. It can be bombarded by other, smaller galaxies. Larger neighbors can gravitationally strip its outer layers of stars and gas, the tidal stripping effect. Flying through the hot intergalactic gas in the center of the cluster, it can be completely deprived of its own cold gas, the fuel for star formation, the Ram pressure effect. Its entire evolution is a story of struggle and adaptation to an aggressive environment. A galaxy in a vacuum field experiences almost none of these external influences. Its evolution is determined almost exclusively by its internal parameters, its mass, rotation speed, and gas reserves. It develops in a clean, sterile environment, as it were. This makes them ideal objects for testing our theories about how galaxies form and live. For example, theorists have models describing how supernova explosions and winds from young stars can regulate star formation by ejecting gas from the galaxy, so-called feedback. In clusters, this effect is difficult to separate from external influences. But in voids, we can observe it in its pure form. By studying these hermits, we calibrate our models so that we can then apply them to more complex cases of metropolitan dwellers. Finally, let's consider another aspect of our special position. The fact that we live inside a void can affect not only our measurements, but also our searches. For example, searches for rare and exotic astronomical phenomena. Take, for example, gravitational waves from the merger of neutron stars. In addition to gravitational waves, these events also produce powerful electromagnetic bursts, kilonovae, which allow us to pinpoint the location of the source. But neutron stars are the end product of the evolution of massive stars, and massive stars do not live long and are born in areas of active star formation. As we have already found out, star formation in voids is slower on average, and galaxies there are less massive. This means that the probability of an event such as a neutron star merger is significantly lower in a void than in a dense filament. The same applies to most other interesting phenomena. The brightest supernova, the most powerful gamma-ray bursts, the most active quasars. They all prefer the noisy, dense regions of the universe. This creates observational selection. Most of the most interesting events that we record occur in the 10% of the universe that is occupied by filaments and clusters. The remaining 90%, which is occupied by voids, remains dark and boring to us. We study the universe by looking mainly at its cities and highways and pay almost no attention to its vast rural expanses. But as we have seen, it is in these spaces that the keys to the deepest mysteries of cosmology are hidden. This is another paradox of our situation. We live in a boring place, which, however, makes our observations of the universe incredibly interesting and confusing.